Hello. Today we are going to dive deep into deep learning and talk about convolutional networks, which once revolutionized the field. Okay, first of all, let's discuss the plan of this lesson. First of all, we are going to listen to a lecture where we will discuss some tasks which convolutional neural networks help to solve, intuition behind convolution, how convolution works in 2D case, and then we will kind of expand that knowledge on real images which have actually 3 dimensions. At the seminar, we are going to implement convolution ourselves in pure Python, discuss max and average pooling, and write a simple convolutional net ourselves with PyTorch. Also, there will be a pretty big homework. The first part includes a lot of information about convolution as a mathematical operation and different applications of convolutions. I hope it will give you a better intuition and deeper understanding. And in the end, you will have to implement some convolutional networks in PyTorch. There's nothing fancy, but it takes a lot of time. Okay, let's start with the lecture. First of all, we're going to talk about different applications and see that convolutional neural networks are a really powerful tool, which is capable of kind of magical stuff. First of all, on the slide you can see classical applications of convolutional neural networks. Of course, first of all, it is classification, the most basic task. Many other applications stem from this one. The second one is classification plus localization, which is just classification when we also find the bounding box for our object. For example, as you can see, the cat here is, we can see its borders. And two other applications are object detection and instance segmentation. Object detection is really similar to classification plus localization, but it's about many objects. It is used when we want just to understand what is in the picture. And instance segmentation not only allows us to kind of make a bounding box, but also understand which pixels belong to a certain class. On this slide, you can see what a self-driving car, how it looks at our world, and it is all done with convolutions. Also, another really interesting application is super resolution. When we take an image which has low resolution, on the right there are 4 such images, and transform it to have higher resolution. Images are on the left. Okay, first of all, we will dive into classification, since it's the most classical and simple task. Okay, we need to understand how computer sees images. We've already worked with them, and well, it's just an array of numbers. 2D array in case of gray images, or 3D in case of colored images. Since, well, colored images, they have X coordinate, Y coordinate, and channels, red, green, and blue. Okay, we have some numbers. Maybe we can just use our old fully connected neural networks and do something with them. I doubt we can, since even for an image which has 128 pixels and it will be 49,152 numbers, which is quite a lot. Okay, what if we just feed it to a fully connected neural network? We will get approximately 5 million parameters on the first layer. if we have at least 100 hidden nodes. And honestly, 100 hidden nodes is not enough to perform such a complicated task. We would need something a lot deeper, and we would have a lot more parameters. And the problem is, such task is too complicated for neural networks. If we tried to train such a network, what we would see would be such a loss plot. It wouldn't decrease at all. Okay, maybe there is something we can exploit about images, some knowledge from outside, which we can transfer to our networks so that they can process images in a smarter way. Yes, there is something. For example, let's look at this network. Fully connected network wouldn't have well, let's take some image. If we shift it 1 pixel to the right, it will stay the same image. We as humans understand this thing. But our neural network, fully connected neural network, doesn't. If we shift our image just 1 pixel to the right, it would show completely different results. It means that we need something which respects which doesn't respect small permutations in pixels, which acts the same in the left top corner or in the right bottom corner, which would classify these cats as the same class. Also, there is one more feature of images which we can exploit, called local connectivity. It's quite easy to understand that for images, the pixels which are closest, they mean they're most connected, they have the strongest relationship. And it means that, for example, at first we can, when we look at left top pixel, we can just forget about bottom right one. But how can we incorporate this knowledge into our neural networks so that they become smarter and operate on images better? Let's turn back to our classification problem and solve the simplest task of classifying gray circles and crosses. As we can see, these two images, they have some special features which the other doesn't have. For example, in case of cross, it has diagonal lines and it has some small cross in the center. If we apply convolution, which is taking this small pattern, 3 by 3 pixels on the right, and sliding it over the image while multiplying it element-wise and then taking the sum, we would get this image, which is on the right. We will dive deeper into how it happens a little bit later. But what is most important is that we can find this diagonal line. As you can see on the pixels which correspond to this diagonal line, the values of convolution is 1.0. And in this way, convolution can help us understand what is in the picture. Okay, let's go to this visualization to get a little bit more understanding. Oh yeah, and also one more thing. In this convolution, the result of convolution is divided by 9, but usually in neural networks it's not like that, so don't be confused if you already know something about convolutions. Okay, now let's look at the visualization. I think that it is really helpful in helping to understand how convolutions work. Okay, this is our filter kernel, or there are many names, but we will call it filter or kernel. This is a matrix, which is kind of a parameter of convolution. When we say that we apply convolution to some image, we should understand which kernel we use at this time. Okay, how the convolution is carried out. We take this small filter matrix kernel and apply it to some part of an image, just like right now. If we do this, the values from the kernel, the numbers, they correspond to some pixel on an image. What we do next is perform element-wise product and take sum of all these numbers. This operation is carried out in the center of the screen, as you can see. If I slide that image, I get something different. And all these values of element-wise product and sum, they are written in the image on the right. Okay, so how to perform convolution? We take this kernel, slide it by 1 pixel to the right, then we go to 1 pixel to the bottom and do it once again. After all these computations, we have this image, which is the result of convolution. I think that it's really helpful to play with this thing all by yourself, to choose different filters. For example, right now it's sharpen filter, and we can use blur filter. And all the computations are the same, but because we changed our kernel, the output is also different. However, if we slide our window, kernel, filter, many names, as I have already said, to the border of an image, some of the values of pixels are unknown to us. As you can see, they're just outside of an image, we don't know them. And it means that we cannot calculate the value of element-wise product and sum at that point, the value of convolution at that point. Effectively, this means that after convolution, our image will be a little bit smaller. And sometimes this is really undesired effect, which can cause a lot of problems. For example, it disables us to find some features on the border of an image. And for really deep neural networks, it causes image to shrink really fast, which is also a undesirable effect. How can we fight with this thing? Well, there is a special parameter called padding. What it means is that we just pad our image with zeros around it. The number of zeros is parameter itself, but usually we take just as much zeros as we need for the image to kind of save its size. However, at this illustration, the image changes its size because it also has a stride of 2. What is a stride? Well, as you can see, the window slides through the image, but it doesn't slide by 1 pixel. When it changes its position, it's changing by 2 pixels. And the amount of pixels the kernel or the filter goes to the right or to the bottom is called stride. As you can see, this is a different illustration explaining what stride is. For example, when we wanted to acquire the value of that pixel, we applied our filter to that part of an image, took element-wise product and then sum. So we got that the value in that red cell. Then we wanted to calculate the value of the green cell, so we moved our filter 2 pixels to the right, because stride is equal to 2. Or if we wanted to calculate the value of blue pixel, we moved our kernel 2 pixels to the bottom. For example, if the stride was 3, then we would have to move that filter 3 pixels to the right or 3 pixels to the bottom. At the visualization we looked at earlier, we applied some predefined filter. But in neural networks, this isn't really helpful. Well, yeah, surely we can kind of invent the filters ourselves, write down those pixels and apply them, but it wouldn't be really useful, since at some point humans just lose their sense of what needs to be done. It wouldn't allow us to construct really deep neural networks. So our filters, their weights, the values of these numbers, they are also trainable. Just like in fully connected layers, the weights are trainable. We can update them using gradient descent. What it means is that the kernel size, the size of this kernel filter or this matrix, is also a hyperparameter, a parameter we choose before training and cannot change during the training. It can be really different, but the simplest, the most basic value is 3. As you can see, it is 3 by 3 filter here. And when we apply it to that image, what we do is we take that square filter, we apply it here, take element-wise product, and take sum. So we get this value. Then we move it 1 pixel to the right, because, well, when we don't talk about stride, we usually suppose that it is equal to 1. And when we don't talk about padding, we also think that we don't use padding. Because stride is 1, we move it 1 pixel to the right, do the same thing, element-wise product and sum of these values. Then we move it to the left and to the bottom, do the same thing, and move it once again to the right and do the same thing and get those values. As we have already said, those filters, they are trainable. And in neural networks, and on one layer, on one convolutional layer, we want to apply many different filters. So if we try to train them on a big enough data set and then plot those first filters of the first layer, then we can get such image. As you can see here, different filters try to find different features in the image. For example, there are many filters which search for different lines. Some of them search for kind of blurry dots or something like this. What it means is that from this thing we can understand why convolution exactly works. Because, well, actually, it simply tries to learn patterns, which it then tries to look for in an image. And when it recognizes the pattern, the activation of a convolution is high. It goes to the next layer and so on. We kind of extract features from our image. For example, if after the first layer, we just get some activations which mean that at this place there is a border, there is a line. The further we go in our network, the more high-level features become. For example, at the last layers, if we use some special techniques, we can understand that separate filters, they can signal that at this part of an image there is a head, or there is a car wheel, something like this. Okay, so far we've been talking about convolutions which are carried out on 2D images, gray images with only one channel. But in reality, we rarely have to work with such images. Most of them will be colored and will have 3 channels, and well, we wouldn't have the input plane, which is 2D image. We would have the input volume. Basically, it means that our kernels, they also have to be modified. And in which way? The most kind of understandable is they also become kernel volume. Now they have the same amount, the same number of channels as the input image. What it does is that it allows such kernel to aggregate information in a certain region of an image from every layer. Let's go to this visualization. I hope it will also be valuable in giving you understanding what really happens. To find this visualization, just click on the link in the presentation and press Ctrl F and type demo. Then the second find it word will just guide you to this thing. Okay, what we have. This is a visualization which shows how convolutional layer works. This layer will have 2 filters. This is the first kernel of the kernel of the first filter and its bias. Yeah, we've just omitted this part so far, but in neural networks we don't only perform convolution, which we're talking about, but we also add one more parameter, trainable parameter, bias, just like in fully connected layers. We also have the second filter and the output volume, which has 2 channels. Why does it have 2 channels? Well, because each filter produces a 2D image, 1 channel for the output. We have 2 kernels, and thus we have 2 output channels. And we have the input volume. The input image has 3 channels, and it's also padded. Let's see how this works. First of all, we take the first filter and slide it across that image with stride 2. When we slide it, we kind of slide 3D filter, 3D kernel through the 3D image. It is really similar to what happens in 2D case. So you can use that intuition to understand that better. And for each channel, for each layer of an image, we have the corresponding channel from the filter, which gets element-wise multiplied. And then we take sum of all of these values. Right here, it would be 27 element-wise products. Add our bias and write down the result. Well, when the first filter is fully operated, we apply the second filter, which does the same thing, but for another channel of an output image. And well, that's how it works. One interesting note is that we had an image as an input, 3D image, and we have 3D image as an output. It had 3 input channels, and we have two output channels. Well, two output channels because we only had two filters. If we change that number to 6, we would have 6 output channels. The interesting thing is that we had an input image and we have output image. It means that we can stack our convolutional layers how many times we want. Well, honestly, before this image gets too small, but we can prevent this from happening using padding and not using other stuff. And using this convolutional layers, we can form really deep neural networks. That's amazing and gives really wonderful results. The reason we needed convolutional layers is that we understood that an image has too many numbers in it. We can't just feed the image to a fully connected layer. And we don't understand how convolutional layers can perform classification. Well, what it means is that we need to shrink an image somehow. There are many different ways, but the standard convolution, especially when we use padding and stride is equal to 1, doesn't make an image smaller. We usually make it deeper. The more convolutional layers an image passes, the more channels it will usually have, since we tend to increase the number of filters in each subsequent layer. But it wouldn't shrink in size, and the number of numbers would just increase. We still are not able to feed this thing to a fully connected layer to perform classification. We need to shrink this thing somehow. There are two ways. First of all, we can use padding equals 0, which is equal to 0, but it wouldn't really help much, since the size of an image would decrease too slowly. Also, we can increase our strides. Yeah, and that's quite viable solution. There are no problems with this, but another method has shown to work better for shallow networks. It is called pooling. Right now we will look at max pooling. There are also many other different types of pooling which we will discuss on the seminar. What max pooling does is it also uses a sliding window. In this example, the sliding window has a size of 2 by 2, and it slides, and it also has stride. The amount of pixels it moves by, usually it is equal to the size of a pooling window, so that when pooling window moves, it never overlaps with its previous position to effectively decrease the size of an image. What max pooling does is it applies that window to an image, takes the maximum value from the window, and writes it down as the results of that operation. Then it moves 2 pixels to the right, does the same thing, and so on and so ever. When we do max pooling, we can also have padding, because, for example, if without padding, this 2 border pixels wouldn't be pooled like at all. What really pooling does is that it helps us to compress the information about image and get a little more shift in variance. Because right now, if we shift our image just 1 pixel to the right, thanks to max pooling, probably most likely the activation after max pooling would be the same, and it won't change how we classify our image. Okay, so far we've been talking about convolution, convolutional layers, and max pooling. Now let's talk about training our network. We want to make our filters trainable, and to do this, we must also choose some loss function. We must be able to calculate gradients to use gradient descent. Or backpropagation, as it is also called. This illustration is made to help you remember how backpropagation works. First of all, we have forward pass. When we calculate the output of our network, we take that output, plug it into the loss function, and then we try to minimize that loss function. What we do is take the derivative of that loss function with respect to each parameter and update it to decrease the loss function. That's it. This illustration shows how to calculate gradients after convolution. For example, let's imagine we have an image consisting of X's, filter consisting of these F's, and the output consisting of these O's. To calculate gradients, we must simply do another convolution, and that's it. This thing is not really important because we use PyTorch and we won't have to calculate gradients ourselves. But it's nice to know. Okay, thank you for listening to the lecture. I hope to see you on the seminar. Good luck.